Okay, test. I'm on the stage. Wait.
Where do you want to
Ah,
start?
don't worry.
Ah,
In the center.
wherever you feel
Okay.
comfortable. Okay, so good morning, everyone. We hope you had a good first day of the school. And today we're going to start the day with Sari van Wittenberg. She is a postdoc researcher here at University of Valencia. Well, she's working in the Park Scientific, and she obtains her PhD in 2016 in the University of Antwerp in Belgium. And today she's going to talk us about remote sensing of vegetation traits and functioning. It is a study inside the framework of future research of the European Space Agency, right? And I give the stage to Shari.
Okay, thanks a lot for the introduction. So good morning, everyone. Yeah, indeed, I'm a postdoctoral researcher in the laboratory for Earth observation, which is located in the Park Scientific. And we are one group, together with 3 other groups, we form the image processing laboratory. So in total, we are about, in IPL, we are about almost 70 people, including, of course, like 5 professors and the whole many the rest are postdocs and researchers. As said, well, I work for a project at the moment for the European Space Agency for an upcoming satellite mission, which is the Fluorescence Explorer, and I will slowly introduce you a bit into this topic. So, okay, this is the first slide. I myself, I'm not a physicist, and this is not so uncommon in remote sensing. We have many fields or many people with different backgrounds working together. So I myself, I studied bioscience engineering, and I have a specialization in forest engineering. Where I had already some classes in my master's on remote sensing, but then later on, I was really interested in plant physiology, and then bit by bit, I got into projects related to the remote sensing of plant physiology. So, what are kind of the major big problems we have to face with, and which this research is framed in, is most of there are two big problems. We have growing population. We have to feed this huge amount of population the coming decennia, the coming decades. And we have only limited resources. We of course we can keep on converting forests to agricultural lands and cutting our forests, but of course that's not very sustainable. And so we need to make optimal use of our agricultural fields and of the resources to put this in the agricultural fields, which are mostly, of course, water and fertilizer. And the other bigger issue that we're dealing with is of course a more warming climate. And we want to also know how good our natural resources or vegetated land, how good is it taking up the carbon from the atmosphere. So different kind of constraints, due to the temperature, extremer events like more droughts, which are going to constrain the carbon uptake or photosynthesis basically. They're going to create dynamics, or at least make in the end that we have changes also in this carbon uptake at a global scale. So we want to also improve how the models that are telling us or that can predict us better how much carbon is uptaken under the current situation and under future climate change situations. Of course, if we want to address this problem globally, we have to look at the problem globally, because it doesn't mean that maybe in Spain or in some countries you're doing well in carbon uptake if another country is or if another country has, for example, more drought events and therefore forest fires. This, of course, all these problems are linked together, so we cannot solve this problem just on a national scale. So what is imaging spectroscopy? What is imaging spectroscopy? As probably, I mean, you're a physicist, you probably know very well. But imaging spectroscopy is basically we are by remote sensing, by the detection, we are looking to the full spectral information and the intensity of the light which is emitted which is reflected from all the different bands. So there's many satellites of course that are looking in broad bands, but imaging spectroscopy is using the information of the full signal. So of course our source of energy that we are using is the solar illumination, and we capture it by different types of sensors. So light, as you of course probably know, light behaves both as waves and particles, and in this sense we measure different kind of we're interested in different kind of spectral regions when we are interested in vegetation. And most of it, we are also interested in the reaction of how the energy is absorbed and how the photons are absorbed and interacting with the specific molecules that are the main absorbers of this light. So this is just the repetition of what you of course know, the electromagnetic spectrum of the different wavelengths and the different energy levels and the size of this energy. What we are going to be now talking about today is about the, let's see if I have a pointer. This one? No. Wait. The top one. Okay. So we are interested. I will point to the middle one. So this is the solar radiance coming to the Earth's surface, like how the sun emits radiation as a black body. Of course, less. This is at top of atmosphere, the higher one, and then the lower one, because of you have molecular absorptions in the atmosphere. There's some energy which is retained, mostly due to water absorption in the atmosphere. And what we're most interested, what the bulk of energy that we are receiving at Earth is in the visible spectrum. And so our eyes are adapted to that evolutionary, but also plants, which have evolved much longer than we did. They have also optimal use of these strong this high energy wavelengths, starting from the UV, but also mostly from the blue. They absorb, and they have many pigments. They overlap in the absorption in this blue region and also in the red region. So this is what we also call the photosynthetic active radiation. So between, let's say, 380 and 710 nanometers, all these wavelengths, all these photons with this kind of energy levels are absorbed by the photosynthetic pigments. So in physics, we describe energy in radiation levels, but when we talk about, or when we want to express the quantum efficiencies of vegetation, we convert this energy to photon flux units. So we are working, basically we measure in the field the radiance levels, but when we want to talk something about quantitatively about the functioning of vegetation, we express it in photon flux units. So you see here again, this is the bulk of energy of arriving to atmosphere, the pigments absorbing. And the pigments absorbing so strong here that here you see in the orange level, you basically see all this energy is absorbed by vegetation. So they make most in the bulk of energy here. Plants absorb like 80% of the light. So this tells you like how much already kind of clear image. Like okay, we have plants make optimal use of all this solar energy. Of course, not all of it is going to photosynthesis. That's the whole thing. So when light is absorbed, what's happening? So molecules, they get excited, and of course they have, due to some internal conversions, they convert the energy to different dissipation pathways, and we normally in absorption spectroscopy you observe all these mechanisms. You observe them by reflected and absorbed and transmitted light, or you get the information of the absorbed light due to transmitted light. Of course, when you on the Earth's surface, we cannot measure the transmitted light. We can only measure the total refraction, and in some cases, of course, if we are interested in also in the emitted radiation, which can be thermal, but it can be also some other event that I will explain you further. So what is the main absorber in photosynthesis? So chlorophyll A is the molecule that is the most dominant molecule on Earth for photosynthesis. What is it doing it? So what is absorbing it? The photons can excite the both blue wavelengths and red wavelengths. All the energy levels in between as well, but they have this two major absorption or electronic states that are compatible, or that are telling you where the absorption takes place is in the blue and in the red. But what is also happening is that due to this, when the molecule, the excited energy relax, fluorescence is emitted also in the red and in the far red wavelengths. So basically from the lower excitation level, due to also some energy losses in between, you get an emission which has this the mirror shape of the lowest excitation level, or the electronic state. And then here you see the shape of the fluorescence emission, which is basically from this energy level coming down. So the molecule does not, we're not only interested in absorption also here in this case, we're also interested in this emission, because emission can tell us something about the excitation level of the molecules. And why we are so interested in that? Because, like I was telling you before, we're interested in the carbon uptake. In the end, photosynthesis starts with these important light reactions, and this is what we can observe from remote sensing. So we absorb how energy is absorbed in these wavelengths, but at the same time, because these energy levels, so I will go to the point again. So chlorophyll is not alone working together. It's working together with many dense other molecules which are densely packed, and making it, and due to this densely packing and the very high efficient transfer of the excitation energy between these molecules, eventually this excitation energy is going to excite a center reaction molecule, a chlorophyll molecule, where a final electron is going to be separated, creating an electron current, which is going to also further lead to the carbon reactions of photosynthesis. So this was very in detail what is chlorophyll doing, but what are we in general, how we try to make algorithms, or how we try to obtain information from the reflected light is basically by calculating the reflectance factor. Here there's the directional reflectance factor, and all the spectral regions that we are interested in. So here before I was talking about the visible, where you have the chlorophyll absorption, but also you have here, so you have water absorption. Also here you have due to structure, the cell structure, and here in the sphere, in this shortwave infrared, you see also here you can obtain information about water content and structural pigments, structural material of the leaf or the vegetation in general. So what are the common, what are functional vegetation traits? Vegetation traits are many things. They can be separated, if you want, in some kind of classification, biophysical, biochemical, biological, geometrical, and geophysical. So these are all kind of parameters that we try to obtain directly or indirectly through the reflected light of vegetation. So some of them are related to specific molecules, like nitrogen, for example, while other ones can be more biological. So if we look to these, some of the phenomena, or this how green is, or vegetation state is changing due to seasonal, by having data over seasonal changes, we can also think about, we are interested in crop phenology, which is the change of or the length of basically of the growing season that we're interested in, for knowing for how much to know how, for modeling how much carbon is taken up during the season. So what are the methods to characterize this? We have different kind of methods, so that are using this that are using the shape of the measured by imaging spectroscopy. And what is the most common and most widely used and most simple and completely not very complicated mechanism is basically by narrow band vegetation indices. So then we're basically using vegetation bands which are sensitive to the absorber, to the driver of the trait that we're interested in, compared to other bands that are less affected by that, and by normalization or by different kind of transformations, all algebraic formulations, we transform them to an index or an indicator which is sensitive to the vegetation trait. So what are kind of, this is the NDVI has been developed already in the 70s, but it's still the most common used in different kind of adaptations to tell something about biomass or greenness or chlorophyll content or many other things. So it's basically using the strong absorption in the red due to chlorophyll, and then the strong scattering due to the leaf material as well. So this shift between the red and the near infrared, which is called the red edge region, this is used as these two bands are used in simple indices to tell something about the amount of biomass. What are other ways to, sorry, apart from simple from vegetation dishes, we can use more spectral transformations. We can use spectral derivatives, spectral integrals of the signal, or we can more use also non-parametric regressions where we feed. We look for how the variation or the covariance is changing with the parameter. We can use machine learning methods as well to put in all the information of all the spectral bands to look to the best regression correlation with our variable. So there are many methods. We're not going to talk too much in detail about them. So what is another issue we have to deal with, because of course we have absorptions happening at molecular level at leaf scale, but at the same time we have also light scattering through our medium, which is then the canopy, and all these kind of other processes that are also happening in the atmosphere. In the atmosphere, the light that is reflected from the top of canopy can still also interact in the atmosphere with the molecules over there. So we have in what you can say we have a scaling problem. Or we have to be able to ascribe these radiative processes from what are happening or what we know what is maybe happening at the leaf scale. We need to be able to understand the processes in all these levels. And for that, we use radiative transfer models. So there's different kind of, there's a huge families of models here, which have different kind of complexities. They can go from 1D models to 3D models, which of course are computationally quite more expensive. And then we have also here the leaf models, and then here the canopy models, and also there are different kind of strategies to combine all these into ones. So what are these models are used for is also to generate some artificial data, which we also use to improve the algorithms for the retrieval of our vegetation traits. Of course, you have to understand. If you invert the models to retrieve the parameters, your retrievals, of course, are only going to be as good as the accuracy eventually of your model. So the idea, the evolution is also there to keep on, improving the forward modeling, of course, with more precise information that we obtain from the spectroscopy data. So I give you here some few examples of the retrievals that we do. So here's one of canopy water content, and here you see this is an example of a spectral integral index where we use here are simulated data from the reflectance of canopies, where we only start driving or changing the water content, and then you see here that this surface here is then used in an index formulation, which is also quite straightforward. But this is then later on validated and used on a field scale, on a remote sensing scale, and here you see an image of agricultural fields in barracks, which are irrigated by this pivotal irrigation system. So you see in the rounds, you can see the water content being different, being higher, of course, than the rest, the dry soil around it. Then there's also here an example of the same region for crop nitrogen content, and this is an example of a machine learning trained parameter. And here you can again see the change or the variance in nitrogen content, but at the same time these models can also provide you some uncertainty, and then you can have both also the parameter map and the uncertainty map of your trait. Then here another example of the leaf area index. That leaf area index is basically the amount of area of vegetation over the area or ground. So the units of LAI is square meter over square meter. And then here you see more temporal evolution. And here is an algorithm that was developed for both a green LAI index and a brown LAI index. So separating between the green vegetation and dry vegetation. So with these kind of algorithms, we are looking into also seasonal dynamics of how vegetation is going through the growing season and how the senescence is happening and when eventually the crop is harvested and the crop is dried out. So how do we test and validate all these things in the field? Well, we measure, of course. So this is not only not only work at the image level, and we measure with spectroradiometers in the field at leaf level. So here are some examples that you can see. We go with different kind of. This is a spectroradiometer. Here in the end, these are the handheld tool to measure at leaf level. Here we measure also at leaf level, but here we use a specific filter to measure, and this is designed to measure this chlorophyll fluorescence that I was telling you about before. And then of course here we need to obtain the incoming radiation, we measure white reference also in the field. At top of canopy, we have also, I'm showing you now a bit like the most advanced instruments that we're using for hyperspectral remote sensing, so where we have all the narrow bands available. And this is what we have now currently in our group, which is a cable cam. And on this cable cam, it's a multi-sensor tool. We have not only a point spectroradiometer for the hyperspectral remote sensing, but there's also a thermal camera and another camera on board which is doing broadband, but which are also overlapping with a current satellite which is already operational. So we are able, in fact, this is our drone, and the same instrumentation that you see here we can mount also on the drone. And so here again you see a diffuser. We have to, of course, we don't measure with this kind of instrumentation constantly the white reference of the incoming radiance. No, we have a sensor here which is the downwelling channel, and we measure through cosine receptor the incoming radiance. So these are an example of an airborne system which has also different sensors on board. And here is also, in fact, this is the current newest sensors that are this is a plane of INTA from the Spanish Institute for INTA. I don't know. I have now gonna come to the name, but okay. So here you can see also here the CAFL, which is also one instrument designed for the measuring of, which is very narrow band for measuring the chlorophyll fluorescence. I will tell you a bit more about that. Okay, this is a typical how the satellite, basically a satellite system works. You have communication, of course, with the ground system, and normally you pass the data that you collect during the day. You go when the satellite is going on the backside or the dark side of the Earth. He's transmitting all the data that are then further processed in on Earth. So two basic concepts for satellite characteristics are the spatial resolution, of course, the same that like a camera. So the higher spatial resolution, the narrow or the finer your pixel on Earth. And the same thing with the spectral resolution. But when we were talking about imaging spectroscopy, we are really always using this very narrow band, and that we obtain the full signal. So this is the type of sensors that we use in imaging spectroscopy. Same thing here. This is called, in the end, for the hyperspectral signals, these are called the hypercube. So the hypercube with all the layers of the different bands. So maybe you can see this is an image presentation, of course, with one with an RGB color, but then of course you have all maybe between 100 and 200 bands here available of information. of how we go to the vegetation functioning with imaging spectroscopy. So not only to the traits, so I was talking before about traits, but now we want to know, okay, but how, maybe you have so much chlorophyll content in the surface, but that doesn't, okay, it tells you something about functioning, but how much detail can you go with that? So what are the basic concepts also already from the 80s to talk about functioning, and are called the light use efficiency models. So they are used, or they are very simple also. A basic approach is to estimate this gross primary productivity, which is the amount of carbon that is uptaken per square meter per year, or can be also in a different kind of units, but it's more or less the flux in this kind of sense. And they make they're simplified, and they make an abstraction of how photosynthesis is working based on these basic parameters. And what is basically assumed that under appropriate environmental conditions, the rate of photosynthesis depends on the absorption of the effective solar radiation by the leaves. And then the solar energy is changed to the chemical energy in a fixed ratio. So we have the fixed ratio of absorbed energy by vegetation of the incoming par. Then there's a kind of potential light use efficiency, which is the maximum one, and another factor which is telling you something about the constraining due to the environmental stress. So at global scale we work, so these are the global scale type of models that work to estimate this GPP. So they're not highly complex. Of course, we can start improving these models, but currently we use, for example, for the FA par, still this NDVI is often used, which is this simple index telling you something about greenness in this red edge shift between the green and the near infrared. So what is still kind of needed to improve what I was telling you before in the introduction, to improve the optic models, is to improve basically these light use efficiency models to get to a better estimate, a quantitative estimate of this gross primary productivity of vegetation. And for that we had already some satellites in the past, but also now currently this is a bit the era we have currently in remote sensing of new sensors that are going to be able to capture the signal at a higher spectral resolution. So currently we have very recently launched an Italian satellite and a German satellite, which have also this narrow band setting. But what I want to do, if I have still some time, I wanted to talk you quickly about the FLEX mission, which we are involved here in the University of Valencia. Which is it's an Earth Explorer of ESA, so basically it's a scientific mission. It's a mission that is going to test several things, and it's not kind of the type of mission that is covering the Earth constantly at a very high spatial or temporal resolution, but we are going to have at least data available at very high spatial and high spectral resolution to measure photosynthesis. So what is so unique about FLEX, which is going to be launched in 2025, is that it's a tandem mission. So it's going to fly together with Sentinel-3, which is another satellite from ESA. And by this we will have basically 2 platforms with in total 4 sensors, and we have all these 4 sensors are covering a large amount of spectral range. So we have in the visible, the near, and the sphere, and the thermal as well, and it's specially designed to measure the solar-induced fluorescence. So solar-induced fluorescence, it's I told you a bit before in the introduction. So we are going to be not only interested in not be able only to measure the reflectance, but by the satellite, by the band setting of the satellite, we're also going to be able to measure the emission. And the emission, it's a very small emission. And that's why the sensor has to be so well improved. It has to be very sensitive. It have very high signal-to-noise ratio, because fluorescence, the amount of energy or amount of photons or it's a relative very small signal. It's only like a 1-2% of your reflected radiance. So therefore, this is a very state-of-the-art sensor. And then another dissipation mechanism that I didn't talk too much about, but is also related to photosynthesis. There's another mechanism in which plant can regulate the excessive amount of energy, and this is called non-photochemical quenching. And this is basically, to be short, I mean, to explain you very in short, are basically other type of molecules which are going to protect. When there's too much light, they're going to protect the excitation energy, and they're going to start dissipating by internal vibrations. And this kind of signals we can also see in the end from the signal, but are also very tiny. So how we can get to, if the signal is so small, this fluorescent signal, how we're going to obtain it is basically we're going to separate in the fluorescent signal, which is a smooth signal with two peaks, from the reflectance based on retrieval methods which are decoupling the reflected radiance and the fluorescent signal. But by that we're using the oxygen absorption bands, which are overlapping in this range, and where the solar irradiance is strongly attenuated. So if we know perfectly, so here in this region there's almost no energy coming to the Earth's surface, but we know if these bands are a bit higher than expected, then we know that this is due to an infilling of this fluorescence emission. So it's basically algorithms are decoupling based on a very good atmospheric correction of the reflected radiance. So these are a bit the band setting I was telling about. These are 4 sensors that will be on board. Very, very high extreme spectral resolution. We're talking about 0.3 nanometer spectral resolution in this sensor that is going to cover these oxygen absorption bands. And then we'll have at the same time a 1 nanometer resolution in this in the whole visible, where we need information to obtain how chlorophyll is absorbing. And then the other sensors are here, are covering also the thermal infrared, which is also important to get a temperature estimate of the surface to constrain the photosynthesis models. So how we can get then, that I was telling you also a bit before, how you can get to from the solar induced fluorescence to actual rates of photosynthesis? Well, it's to be able to disentangle all these energy dissipation mechanisms to eventually get to what the unknown, which is the photochemical regulation. So the flex mission concept, or the tandem mission concept together with Sentinel-3, is able to get an estimate from the reflectance to get a better estimate, quantitative estimate of the absorbed energy by vegetation, and also for the photochemical energy dissipation due to other molecules also through the reflectance, but looking to how certain molecules are changing this reflectance spectrum due to the changing the absorbance, of course. And eventually all these models, there's already kind of links between these are the light reactions that are feeding this biochemical reactions and eventually to carbon assimilation. Those are going to be plugged in, the new traits, the dynamic traits that we're obtaining here are going to be plugged into biochemical models to be able to get a very more precise and quantitative estimate of this carbon assimilation. So this is my last slide. So what is kind of a bit the road to improving this carbon uptake modeling? It's to get, so we have instantaneous, we'll have instantaneous overpasses or images from these dynamical traits, and then by doing temporal and spatial composite processing of more data, we'll be able to get mosaics, not only spatial mosaics but also temporal mosaics that tell us something about about different kind of spatial, about the stress or the how you say, like the change of the different parameters in due to different kind of temperature, water conditions. So these new traits will be make full use of this this imaging spectroscopy information, which is not only getting better information, quantitative estimate of the absorbance, but also of this emitted light, which is the fluorescence. And these are going to be able to improve the carbon modeling to be able to get better estimates of the carbon assimilation. So this is a bit was an introduction to what we're doing in LEO, which is Laboratory of Earth Observation, in the Parc Scientifique. We are doing many other things, but most of the things I think I covered a bit in the presentation. So there are people working on this theoretical modeling from radiative transfer processes. There are people working on new instruments and techniques. Retrieval techniques for improved estimating of quantitative traits. So it's quantitative remote sensing. We're doing really into not kind of any kind of, we're not interested in many relative or very qualitative parameters. We're very interested in very better improved estimates of not only of chlorophyll but also how the chlorophyll is absorbing, and in the quantum efficiencies of these pigments. So these are we are involved in several projects which are related to several satellite missions, but most of them we're interested. We're focusing on ESA missions, which are FLEX and Sentinel-2. So at the same time, we're also we're involved in a master and PhD here at the University of Valencia, which is called a master in teledetection. And that with that, I want to finish the presentation. So if you have any more questions, please let me know. I hope I was a bit in time. And yeah, thanks for your attention a lot.
So if anyone has any question, please raise your hand.
It's too early.
So I have one question.
Yeah.
I'm fascinated how these very small processes that happen in the plants have an effect in the global scale.
Yeah.
So I was wondering if there is any microscopic model of photosynthesis or something like that from which you can extract information about the global effect of photosynthesis.
Yeah, so I was trying to mention. So you have, of course, models that are linking these light reactions to the carbon reactions, but even at let's say even at leaf scale or molecular scale, there's also still there's a lot of people working on how energy is eventually getting to these reaction centers, but in a quantitative way, making optimal use of all the signals. This can be still improved. So there's still a lot of, photosynthesis, there's many research on photosynthesis at different kind of levels. There's people working in the lab really in vitro at molecular scale, but there's indeed still, there's many research going on to improve these models and to quantify better how much energy is eventually triggering the carbon reactions. Yeah, but in the end, this is the beauty of this satellite mission. In the end, it's very challenging but we assume that these small changes in this change in the light reactions that we hope to see from space. But even my work is the fact that I'm looking at these things at leaf level. So the challenge will be because you have a whole atmosphere which is modifying your signals. The challenge is that the atmospheric correction to get to the ground signal at a very high precision.
Thank you. Any more questions? So if not, thank you again.
You're welcome.
Our next speaker is Miha Papic. He comes from Slovenia, the city of Ljubljana. He studied his bachelor degree in the University of Ljubljana. And then he moved to Munich in Germany to study his master thesis. He focused on noise models on superconducting qubits. And then he moved to work for a quantum company here in Europe. It's a leader in this field of investigation, and he's doing an industrial PhD in this company. So, well.
Do you need the microphone?
Yes.
Okay. Okay, is this thing? Yeah, I think it's working.
Yeah, it works.
Okay, yeah, so thanks for the introduction. So yeah, my name is Micha. I'm doing a PhD at IQM, so I came as a company that builds quantum computers here in Europe. I think it's the only one that's actually building quantum computers. And I'm doing a PhD jointly with the University of Munich or the Ludwig Maximilian Universität, if you ever see that name pop up. So what I wanted to talk about today is basically, today when quantum computing is this big thing, there's a lot of hype around it. And one of the best ways to do quantum computing currently is using superconducting circuits. And what I wanted to kind of explain or briefly illustrate today was how do you use superconducting circuits to actually do quantum computing? Because this is a concept which is not maybe that trivial, how to actually make a qubit. Sometimes we talk about quantum computing in this abstract space, but we never really ask ourselves how do we actually implement these systems. So this is maybe one I wanted to talk about today. So, but yeah, to start from the basics, so all of today's computers are based on classical information, classical bits. So classical bit is a pretty simple thing. It's an object which is either a 0 or a 1. It has two possibilities, 0, 1, up arrow, down arrow, whatever you want to choose for your notation. It really doesn't matter. And then you can encode information with classical bits. For example, this is a very trivial example. You can say that, okay, this year, which is written like this in our decimal, regular representation, you can write it in terms of classical bits like this in a binary representation. So this is how a computer is stored in your regular, this is how information is stored in your regular computers. So maybe the next step that you can make is do a probabilistic bit. So this is kind of a concept which has existed now for a couple of years, but it's not that big yet. So this isn't something that you're going to encounter in your daily life, but it exists. So probabilistic bits are basically bits which are kind of random. They jump between these two states. So these jumps are completely random, but on average, if you observe this bit for a long amount of time, you can see that, for example, this one here, on the slide, half of the time it's up, half of the time it's down. So this is basically, a representation of the number 1/2. And this is, already a bit more complex than a regular classical bit. So it has some drawbacks, it has some opportunities. It's one potential way to do computation. And you can also obviously represent other numbers in this way, for example, 1/4. You could write it in terms of, if you just have to observe it for a set amount of time and then average over, the time that the bit is in the up and the down position. So it's a simple concept at the end of the day. And then obviously the next step are quantum bits. So this is now a big kind of jump in terms of complexity. So quantum bits are no longer described by simple things such as the amount of time that's in the up state, the amount of time that's in the down state. What you need to describe the quantum bit, and there really is no classical analog for this, is a quantum superposition. So a quantum superposition, you will typically use this notation. This is just an example. So the bit is in the state down and the state up, and it is in this with an equal probability. This is given by the fact that there are no different weights in front of these two states. And you can write this even more generally. You can parameterize it, but this is the most general way that you can write the so-called wave function, the state. But this is how you describe the quantum bit. So like I said, I was really trying to come up with a classical analog for this, but obviously because this is a quantum phenomenon, there isn't going to be a classical analogy for this thing. But maybe to better illustrate the differences between these kind of ways of doing computation, we can just look at some pictures. So this is a line. And a classical bit can be represented like this. So there are 2 points. So these are, okay, so here there's spheres, but you really have to imagine 0-dimensional objects here. So it can be either up or it can be down. And it cannot be anywhere else in between. While the probabilistic bit can now be, sometimes it's up, sometimes it's down, but it can be on any point on this axis. So already the probabilistic one is we switch from 0-dimensional objects to 1-dimensional objects. And what quantum bits can do is they basically go into this actually 3-dimensional space, but they are limited to the surface of the sphere. So because this is a surface, this is still a 2-dimensional object, even though that you need 3 dimensions to really describe it properly. What's also interesting to see here is that there is an overlap between the qubit, so the sphere, and the classical bit. So this obviously means that the qubit can also behave as a classical bit. So we can use qubits as classical bits. But the thing is that there is no reason to do this. It's just stupid. If you have a qubit, you have to use the fact that it's a qubit. You have to use the fact that that it has this possibility of superposition. And these superposition states would be somewhere on this part of the sphere, which is far away from this z-axis, which classical computation enables us to use. Okay, so this is kind of like a very short introduction of what a qubit is. Now let's I'm going to try to convince you why qubits might be useful, not on a scale of a single qubit, but on a scale of more qubits, why you would need this, why you would actually need a quantum computer. So all this like hype about quantum computing began basically years ago with these two big algorithms I want to just like show you today, because they're, in a sense, they're pretty simple ideas. We're not going to go into the details, but the first one is so-called Grover search. So the problem here is pretty simple. We have this list of boxes, and what we want to do is find this green box. And obviously, we can't look at the whole list at the same time as is shown on this slide. We have to look at each individual box, and this is going to take some time on our classical computer. So classically, what you have to, so as I mentioned, you have to check every single box in this list. Is this box green? And then you say, no, this box is not green, we need to move on. And this is going to take some time. Now, if this list has five elements, this is going to take a negligible amount of time. But if I give you a list with 20 million elements, it's going to take some time also on your laptop. So if we then increase the length of this list, it's kind of obvious that we're going to need twice the length of the list, twice the amount of time that we're going to use, because we still need the same amount of time to check every single box. So what we're going to describe this is as a linear scaling of the complexity of the algorithm in a classical sense. So what I mean by complexity here is just like a rough estimate on how much time your computer is going to need, depending on the size of the problem. And the size of the problem here is really just like the length of this list, so all of the boxes that exist. And quantum, well, quantum can do it in square root n. So this is quadratically faster. And then obviously I'm not giving you enough information to really understand this result, but the more, at least when I saw this for the first time, I thought it was, okay, this is kind of magic. So this was like Grover search. There's another algorithm which is very kind of important called Shor's algorithm, which is used to factorize numbers. So you start out with a number like this, and then you want to write it in terms of a product of prime numbers. And the reason for doing this is because it's used in some encryption algorithms today. So stuff like that makes it very, very important to also see if we can compute this in a more efficient way. Because if we can compute these factorizations in a more efficient way, there are some possibilities to use this. And so again, if you go for a lot of theory, you're going to get this result for the classical complexity of this thing. But quantum can do it in this. And if you compare these two numbers, this is now exponentially faster. And as you all know, as kind of physics students or possibly soon to be physics students, an exponential function is something that really rises very, very quickly. And what the size of the problem here is literally the size of the number. So everybody can factorize, for example, the number 8, that's 2 times 2 times 2. But if I tell you, okay, factorize 15,513,000, that's more of a difficult task. So that's why it's a tricky thing to do. But the takeaway message here is that a quantum computer has this potential exponential speed up in terms of breaking the encryption of some data. The good news is that this is not going to happen anytime soon. This is something that we're probably going to have to wait for years and years and years before we're going to have a quantum computer which is big enough to really compete with a classical computer in terms of this specific algorithm for factorization. So okay, hopefully now I convinced you why you would want to make a qubit, why you would want to make a quantum computer, but now we have to ask ourselves, okay, we want to make a quantum computer, what kind of criteria do we need to have, what are the properties of the system where we implement this quantum computer are? And so Professor De Vincenzo thought about this already years ago, and he came up with this kind of list of criteria that our system needs to have so that we can do quantum computing on it. So the first one is that it has to be a well-characterized qubit, so we have to know what the 0, 1 state are, what the down arrow, what the up arrow is, whatever. This is, I think, kind of obvious. And it has to be scalable, so we have to at least have the potential of being able to construct a quantum computer with millions of qubits with this technology. The next one is that we have to know before we do any operations on a computer, what's the state of the quantum computer? What's the starting point? Again, this is kind of obvious that you have to know what the initial state of the quantum computer is before you do anything. So again, nothing really groundbreaking here. So the next one is at low noise levels. So again, obvious. You have to allow operations on your quantum computer. So as I said, you have to be able to perform a set amount of operations which have to be general. So that if you can only perform operations on one single qubit, then it doesn't make sense to have 1,000 qubits if you can't actually do operations on more than one, because then you just have 1,000 separate qubits, for example. And obviously, we need to be able to measure whatever we computed. Obvious. What is not obvious is like doing a combination of these three. So this is kind of the paradox of constructing a quantum computer. So if you want a system which doesn't have enough noise, this means that it's isolated from its environment. But if it's isolated from its environment, how are we going to measure it? How are we going to control it? So we need to kind of find a sweet spot that enables us to do all of these three things with reasonable accuracy. But again, as I mentioned, these three things are mutually exclusive up to a certain degree. And there's like different ways where you can do quantum computation. So you can use, for example, these trapped ions or neutral atoms, stuff like that. This exists. So you literally use sodium ions. You can perform some operations on them with lasers, stuff like that. You can use just electron states and semiconductors. It's also a very popular thing nowadays. Recently, photonic quantum computing has emerged as like with some very, very nice results. So here what you have is like literally optics cables, so sending single photons. And these are then like operations between the two photons, so you can use that. But what has been kind of the leading technology in the field are superconducting circuits. So this is a figure taken from a Google paper, where this paper was like a big thing back in 2019, where they claimed that, okay, this is the first time that we used a quantum computer to come up with a result which we are not able to compute classically. So this was what they call the proof of quantum advantage. This has been kind of debated about since then, so it's not completely clear. So the algorithm that they performed here is completely useless for every practical task, but they just wanted to use it to show that we can do something that we cannot compute classically. And if you go into that paper, you're going to see the schematic. So this is the chip that they have, and this chip is supposed to contain this. And they have this, pluses, a qubit, and then you have these couplers. So what I wanted to basically show you today are what are these pluses here. What's actually going on here? What this is. Now, in order to understand that, we first have to look at some very simple classical physics results. So this is like the most simple circuit you can basically come up with. So you have an inductor here, you have a capacitor here, and there's some kind of current flowing between the inductor and the capacitor. And then we can write down the regular Kirchhoff's relations. So the current flowing from the inductor to the capacitor has to be the same, because where else should it go? There are no voltage sources, there are no batteries here, so the drop in the voltages has to equal to 0. And we know that the current is just the time derivative of the charge. And then if you combine these equations, what you get is this differential equation, which obviously has to ring a bell in your head. Okay, this is just a harmonic oscillator. It's actually better than this regular pendulum that you're used to, because a pendulum is a harmonic oscillator only in this limit of very, very small oscillations, but this is a perfect harmonic oscillator. So it has sines, cosines as the solution, and it has this characteristic frequency which describes the system. And then we want to compute the energy of this. So the energy is just given by the energy on the capacitor and the energy on the inductor. So again, classical physics results. And then we can rewrite this in terms of a different variable. So this, I hope you can see it because it's kind of at the bottom of the slide, but this phi of t is just like the time integral of the voltage. So again, we just rewrote the result in terms of a different variable. We didn't do any fancy math here. Actually, I see that there's a mistake in the slides. This should be a 1 over L, not a L here. So I'm sorry for that. Just noticed it now. But if you look at this expression for the energy of this circuit, what you see is a time derivative of a variable and then the variable squared. And then you want to kind of compare this to basically a 1D particle in a harmonic potential. As you can see, this is the same thing with the same mistake from the previous slide. It should be 1 over L, but sorry for that. So again, this is a perfect harmonic oscillator, so it has the energy which looks like a harmonic oscillator, obviously. And now we want to make this circuit quantum, because we want to do quantum computing. So when quantum physics happens is usually when the temperatures are very, very low. So we're going to put the circuit into a fridge, and then let's see what happens. So if we then look at the temperature, as we decrease it gradually, first we're going to go into the superconductivity regime. So superconductivity, we're not going to go into the details here. It just means that the resistance of the wires is equal to 0. It's not close to 0, but for all intents and purposes, we think it's actually equal to 0. And this is something that I've been already kind of assuming in the previous slide because there were no resistors in the circuit. So basically, this superconductivity doesn't really change the analysis that we've done so far. But the next thing that happens, if we go to even lower temperatures, is so the temperatures which are kind of comparable to this characteristic energy of the circuit, is that the circuit starts to behave in a quantum way. So what does quantum actually mean? So what does a quantum circuit actually mean? So if we again plot this potential energy of the circuit, what we're going to see is that there are distinct energy levels. So if you're going to look at the spectrum of the circuit, you're going to see this distinct peaks. And these peaks basically correspond to these like special oscillations in the circuit. And the fact that these special oscillations exist, this isn't a quantum effect. So this also exists classically. Like for example, you can compare this to like a string, which has these eigenmodes. So like eigenmodes, eigenenergies, whatever. These are the terms that you're going to typically encounter in the literature. What is really quantum is that, for example, you're going to have this, even the zero state, which should have zero energy, has a small, shift. So it has like a finite energy here. And this is like really a quantum effect, which really tells you that there is some kind of uncertainty principle happening here. Because if the energy was actually zero, then you would know that this, integrated voltage is exactly equal to zero. But because of quantum mechanics, because of uncertainty, we can never say that something is exactly equal to zero. So for example, the most quantum effect that you see here is that the fact that these energy levels are kind of shifted upwards a bit. And then obviously you have these like states. And these states have, the same energy difference between them. And then can we now say that this is like the zero energy, so that this is a qubit? Now this is a 0, this is a 1. Can we use this as a qubit? Actually, it turns out that no. What's the issue here? The issue is that all of these energy levels, because the difference is the same, there's no way to control only one single energy level. If we send in some energy into the system, there's no way to say that, okay, we're now going to excite the system from the 0 to the 1 state, because we're also going to excite it from the 1 to the 2 state at the same time. They're completely indistinguishable for all practical purposes. And then we can, then we can upgrade the circuit a bit. Let's think about adding resistors. That's not going to help us at all. Again, you can think about this analogy with classical oscillators. If you add a resistor into a classical circuit, what's going to happen is that you're going to lose energy. You're going to dissipate energy. So we don't want to lose energy, because losing energy is a bad thing, that this is basically noise. So you can then think about, what if we use different combinations of inductances, capacitances, but we're never going to be able to break this curse of a harmonic oscillator. We might construct a harmonic oscillator in more dimensions or whatever, but we're never going to lose this harmonic potential that we have here. And this harmonic potential that we have is really the reason why we cannot have different energy levels in this simple circuit. So if the issue is the fact that we have a harmonic potential, then we just need to modify the potential, right? And the way that we do this is, so this was a Nobel Prize back, I think, in the 70s for this. I think Mr. Josephson here, he got half of it. The other half was for the experimental proof of this. So he basically thought about the system. So this is like a theorist's idea of what a Josephson junction is. So you have two superconductors. Again, this means that there is no resistance in these wires. And there is a very, very thin insulator in here. And classically, if you have an insulator between two wires, there is no current flowing through this, because it's an insulator, right? This is by definition. But what happens in this quantum, world is, first of all, that these electrons, they're going to bind into these so-called Cooper pairs. So, so that I'm not maybe too abstract here, the reason why, electrons, which should, be repulsed by each other, so because they have negative charges, is the fact that they're in a lattice. A lattice is full of positive ions, and these positive ions are going to basically cause the electrons to form these pairs, and this is what the basis of superconductivity is. And what's going to happen to these Cooper pairs is that they're going to tunnel across this junction. And why are they going to tunnel? Because this insulator barrier here is very, very thin. We're talking about a couple of nanometers here, or this is kind of the length scale that we're looking at. Or you can imagine this with waves, because of the particle wave duality, as an incoming wave, and then it tunnels exponentially into the other side of the superconductor. And what Mr. Josephson did is basically he derived this relation for the current flowing through this junction. So again, writing it in terms of this integrated voltage, you have this result for the current. And how I like to interpret this is even if the voltage currently is 0, if we send a voltage pulse into the circuit at one point, so the voltage was non-zero in the past, but it's 0 now, the current is still going to flow because this phi is not equal to 0 anymore. And it's going to flow because there are no dissipative elements in the circuit, because everything is in a superconducting state. And because it's in a superconducting state, nothing is really breaking or stopping the flow of Cooper pairs. The only thing that's really stopping it is this insulator barrier, and obviously not many Cooper pairs can tunnel through this, because that's the point of having an insulator there. So it has to kind of saturate at what we call the critical current of the Josephson junction. Now, so this is kind of the way that this behaves. There are also like very other useful properties how to use this. For example, if we say that we add a constant voltage, so this U of t is a constant, what we're going to get here is a basically perfect harmonic current. So this can also be used to generate, gigahertz type, basically alternating current. The issue is that these currents are typically pretty small because, again, this is quantum, this is cold, this is very, very small, so, practical usages are kind of limited. But it's still a very, very useful thing, and people use it in many, many different applications. So you can also imagine this is a nonlinear inductor, with the inductance being dependent on the history of the voltage. So that's also one way of interpreting these Josephson relations. And then what we want to look at next is what's the energy of this junction. And again, I hope you can see it because it's kind of at the bottom of the slide. So the energy is always given by this integral of the current and the voltage over time. And then we can just use these relations here. We can rewrite it in terms of this integrated voltage. And what we're going to get is like the integral of a sine as a cosine. And so this potential is now, so we can see that this is like now a cosine function in terms of the energy. And this is what we're now going to use to modify our potential, right? So let's maybe look at this circuit. So this is our Josephson junction. I use this like crossed out box. This is one possible symbol, and a capacitor. And the energy of the capacitor, so sorry for using this letter H. This is kind of a quantum way of labeling the energy, let's say. So the energy of the capacitor is still given by this regular result. But the energy of the Josephson junction we derived in the previous slide. And we can again interpret this first thing as the kinetic energy, and the second one as a potential energy. And then if we plot the potential energy of this circuit, it has this cosine shape, right? Minus cosine. And a cosine is very, very close to a parabola, but it starts to differ from it, like as you get close to the extrema. And you can see that like the energy of these like special oscillations in the circuit is going to start to differ from the harmonic oscillator result, the higher energies that you have. And now we can use this as a qubit. Because now we have like a 0 state, we have a 1 state, or this is like the down arrow, this is the up arrow. And all of these levels here we're just not going to care about. So the first kind of takeaway message from this lecture maybe that you could have is that like qubits don't really have 2 levels. They have 2 levels that we want to use, but there are typically also other levels in the system. For example, like these higher excited states of this circuit. So yeah. Okay, so we can make a qubit. We have 2 well-defined levels. That's like the first DiVincenzo criteria. Now we need to think about controlling our qubit. So let's just look at a single qubit for now. So again, everything has to be very, very cold. So this is like a dilution refrigerator. This is where we actually put the circuits that we've been looking at. And if we want to do gates, what we're going to do is something like this. We're going to have a room temperature voltage source. And then we're going to connect it to some wires. And the wires you can see actually here. They go down like to the qubit circuit, which is somewhere down here. And we're going to just couple it capacitively like this. So this is, regular electronic stuff, nothing really fancy going on. But what is kind of interesting to see here is that you have different stages in the dilution refrigerator. So this is actually like a photo from like one of IQM's labs. So each stage gets like a little bit colder. And once you get to this like really, really cold stage where a quantum computer actually is, you're basically, I think, colder than outer space also. So they're really low energies that you have to be at for having superconducting qubits. And which is obviously one of the issues with using these circuits, right? So then if you want to do like operations on a single qubit, if you want to move around that 2-dimensional surface of the sphere, what you can do is just like send different pulses from here into the qubit like this. It's going to look something like this, so it has a harmonic pulse in a Gaussian envelope. And then you can drive this transition from the 0 state to the 1 state, but you want to avoid this. Again, we want to ignore all higher energy levels, which are not the qubit levels. But unfortunately, that's not always doable. And with this way, we can generate these rotations on the block sphere. They look like this. We can choose it if it's around the x-axis or it's around the y-axis. We can do both. So this is a pretty nice way of controlling the qubit, because if you have x and y rotations, you know that you can construct any type of rotation on a sphere just by using these 2 rotations. So we can control a single qubit basically in any way we want with this. But what's maybe, let's maybe skip that slide, but what's maybe more interesting then is like if we move on to more qubits, because as I mentioned, we don't, like having isolated qubits doesn't like really make sense for quantum algorithms. So when we start talking about like many-body quantum physics, a very, very important phenomenon is so-called entanglement. So we talked about superposition as a very, very quantum thing that we use in quantum computers, but an important aspect of the advantage of quantum computing is also superposition. And superposition, like the concept is pretty simple actually. So for example, let's have two qubits. They have their own states, which are written like this, and then you multiply these numbers, and you get like at a two-qubit state which looks something like this. But it turns out that like you can't do this always generally. So if you think about all the possible coefficients in front of these states, they are not necessarily always written in terms of a product of two independent qubits. And we want to generate states like this. This is where quantum advantage actually comes from. And in order to do this, we keep things simple and just do something like this. So the qubits are now connected with a capacitor. But the issue is that we want to do gates. So we want to turn on a gate, and then we want to turn it back off. So how do we do that? So kind of the classical analogy of this thing is something like this. So you have two oscillators. And again, think about the fact that this is not a perfect harmonic oscillator. This is, it's a perfect harmonic oscillator for just like very, very low amplitudes. Kind of like the superconducting qubit. It's a very, very similar thing, basically. And what we can then do is these two qubits have different frequencies. And what we can then do is just like add a drive. So with that capacitor from the outside world connecting, and we can drive it harmonically just like you would do for a single qubit operation. And again, you can imagine that, think about the classical result of a driven harmonic oscillator. In the long time limit, if you drive a harmonic oscillator, it's going to oscillate with the frequency of the drive, not the frequency of the oscillator. So if we drive this qubit with the frequency of that qubit, then we're going to have two qubits which are on resonance. And if they're on resonance, they can interact very, very strongly. And they're connected with this kind of wire thing, or you can imagine it as a spring. This is what this capacitor basically behaves like. So then if you want to be even more fancy, what you're going to do is this. So you're adding a resonator circuit in between the two qubits. And the reason for doing this is that you would need to add another pendulum in between here. The reason for doing it is that you can turn off the interaction more efficiently than with this like simple example of just doing this. But you can see that like in principle, it's very, very easy to connect these circuits. Just do a capacitor. So now if we have the theory to know how this should work, we need to implement it in the lab, right? And this is actually like a micrograph. This is a superconducting qubit. So actually, this is the superconducting qubit part. And you can see that it's a bit different from what I've showed you previously, but it has the same elements. So it has like a capacitor here. This is a Josephson junction. This one has two Josephson junctions, but it doesn't really matter. The behavior is still the same. This is the capacitor, coupling it to the outside lines for single qubit operations. This is the capacitor for coupling it to the neighboring qubit. And this is for the readout. So we haven't discussed the readout here at all, but you saw that it's one of the De Vincenzo's criteria. So we need to be able to read out the qubit, and that's why we need also like this thing. And because we need these, kind of 1, 2, 3, 4 things, that's why it has this like, X shape. But you can see that it's like pretty different already from, the circuits that we were looking at. And the reasons for this is that like the circuits that we've been looking at, they're models. So sometimes we think about these circuits as being like completely real, but they're not, especially on this like very, very small this is not a microscopic level, so the size of this you can see is like, micrometers, so this is like a 200 micrometer scale. So there are some things which this circuit model, so this, what people will call the lumped element model, are not going to predict. And one illustration of this is this thing. So what is happening here is that we're sending an electromagnetic pulse into one of the qubits. So I highlighted the qubit with this, these red circles so that you can see them better because they're kind of small. And somebody solved all of these Maxwell equations in this chip. And what you can see is that like the electromagnetic field coming in this line, through this line, is actually not only localized here. There's a bit of leakage to the other lines, right? So basically when designing qubits, these lumped elements, they're useful for us to understand what's happening. But if we actually want to design a quantum computer with hundreds and thousands and millions of qubits, what we need to do is something like this eventually. Because we need to check that the operations that we're doing on the qubits are really like well localized? Is there like electromagnetic leakage, stuff like that? How does the readout work? There's a lot of different things that can go wrong when you look at simulations like this. But these things are kind of easier to understand. That's why we use them. And that's why when designing novel qubit types, so things that have more complicated circuits than this, that's why we still like to look at lumped element models. Okay, so this was kind of like what a superconducting qubit is, how it works, kind of a brief illustration of how we can do operations. Like I said, we didn't talk about readout here because that would deserve a lecture in its own, because that's a very complicated thing, because measurements in quantum mechanics are very complicated. So I just wanted to tell you what's the current status of quantum computing as of, kind of this moment. So the largest quantum computer based on superconducting circuits is 127 qubits. And they can live for about half a millisecond. So this is already pretty long, because typically for doing a single gate, you're going to need maybe hundreds of nanoseconds or tens of nanoseconds. So this is already like a pretty big system, and there's like room for optimizing this more. But in order to have like really practical quantum computing applications, a very optimistic result is that we're going to need at least 1,000, like a couple of thousands of qubits. For things like the factorization algorithm that I showed you, we're talking about million qubits at least. The reason for this is that qubits are noisy, and we need to correct them. And if we need to correct qubits, we need actually more qubits. You need to do a thing called quantum error correction. And quantum error correction actually means that you're going to say that my logical qubit is actually composed of 5 physical qubits. And that makes your system size even a bit bigger. So the challenges that are kind of here and need to be addressed in the future are, first of all, we need to improve the way how well these systems work, how well we can do the gates with what kind of accuracy. We need to improve the qubit lifetime, because more lifetime means more operations, means deeper circuits, more entanglement, less classical behavior of the circuit. And there's also a very specific thing about superconducting circuits is the fact that they're in a dilution refrigerator at 15 millikelvin. And the more qubits you put in there, the more electrical power you actually need to cool the circuit down to 15 millikelvin. So there is kind of a fundamental limit in terms of how many qubits you can actually put into one single fridge. The good thing is that there have been some very nice ideas about like connecting different dilution refrigerators with photonic cables, stuff like that. So this is there are ideas of how to deal with this, but nobody has really implemented them yet, because we don't have systems which are big enough for this yet. And like kind of as a summary, what I wanted to kind of illustrate today is that superconducting qubits are basically just superconducting electric circuits. They need to be superconducting because if they're not superconducting, we're going to have losses, which are going to destroy our qubits. And we need these nonlinear elements, so these called Josephson junctions. You could, in principle, use a different nonlinear element, but Josephson junctions are something that works well, so there isn't really no reason to move on to something else. And then if we want to do single qubit gates or operations, we just send an electrical signal to a circuit. It's as simple as that. And we can connect to qubits. We can entangle them by just connecting the circuits that represent the qubits. And what I wanted to kind of like really also illustrate is the fact that these lumped element models can have some unintended, they can be too simplistic at times. There was also like a very interesting, I think, YouTube video some time ago from Veritasium with this like thought experiment of a circuit which has wires which are like a light second long, and then you're going to see that if you look at the time behavior of the circuit, this lumped element model is going to completely break down. It's going to not predict everything that you want. So yeah, this was everything from my side. Thanks for your attention, and I'm going to be happy to take any questions.
Questions? Yes.
First of all, thanks. It's very interesting. And I was wondering why I couldn't get why the LC quantum circuit couldn't work. Because thermodynamically speaking, when you are a very low temperature, you are pretty sure where the population is, most of the population is. But you said you cannot be sure when you send a photon to the oscillator, which state you excite.
Yeah, so I can go maybe back to that slide specifically, If you just like give me a second to scroll through everything. So the issue is this. This thing when you do the pulse, right? So yes, you do know that actually with temperatures which are as low as 15 millikelvin, the circuit is going to start out in the zero state, almost completely. But the issue is that when you want to control it, so when you send a photon in, if these energy levels are resonant, this photon is going to like excite this state from here. And then if you want to send another photon in, you can also like, and if you want to go from here to down here, you also need to like send a photon in. But in a harmonic oscillator, what might happen is that you might go from here to here. And now you're in the 2 level. So you're in the double excited level, which is outside of your computational subspace. And this is now this is a source of error in your quantum computer. The issue is that like as you send a signal like this, it does not only have one frequency in it, because it's a Gaussian envelope. It has many frequencies. And some frequencies are resonant with this transition. So these levels do have still an effect, practically. We would like to ignore them, but it's not always possible. But the issue is not in like us knowing which state the circuit is in. We know very well for resonators what kind of states they're in. We just don't know how to control them efficiently. How to only limit ourselves to these 2 levels.
Okay, now I get. Thanks.
Any other question?
I was wondering about the cooling system.
Yeah.
How does it function, and what's the impact on the power supply of the system?
Cooling. This would be another lecture on its own. Basically, from a very, very high level, what you have is liquid helium, and you have 2 different isotopes of liquid helium. And these 2 different isotopes, they tend to separate if you like. They're liquid helium, so if you pour one on top of the other, they're going to form 2 layers. But if you mix them together, what's going to happen is an endothermic reaction. And because it's an endothermic reaction, it's going to, it's going to get heat from the environment, and the environment in this case would be the qubit, so it's going to cool down the qubit. But basically, you have this mixing of these 2 isotopes of helium happening like down here. There are other stages of cooling which work in different ways, but in order to really get to this 15 millikelvin temperature, you need this like superfluid helium, and this is then also very expensive to make, because helium isotopes are not something that you can just like get from a chemical reaction easily. And yeah, just 15 millikelvins is just very, very cold. So yeah. But basically, this is called a dilution refrigerator, if you ever want to maybe Google it or learn more about these cooling mechanisms.
Okay, thanks.
So, hi. For the lump modules you showed the leakage you have. Do you have a way to control the leakage or no, to keep it on the wire?
Yeah, so maybe I'm going to go to one of my backup slides. So this one. So what we do is you send a pulse, which is like kind of has a Gaussian envelope, some kind of carrier frequency. And this carrier frequency, let's not think about now, because it's just going to shift this. Now, sorry for everybody who hasn't done Fourier analysis yet, but if you look at the Fourier transform of a Gaussian, you can see that the more localized the Gaussian is in time, the less localized it is in frequency. So that's going to cause these additional frequencies which are resonant with this transition. So what you then need to design is a pulse shape, which looks more kind of like a Gaussian, but it has a kind of a 0 somewhere here. So if you look at this Fourier transform, which is plotted here, it has to have a 0 like this, and you can do that. This is called optimal control. There's also other things happening, like as you send the signal down these cables, it's going to be distorted a bit. So what you're going to typically use, or what's very popular now, is to use kind of machine learning techniques to design the pulse. So basically you send in a pulse, you see how well this pulse worked, and then you adapt it based on the results. But in principle, yeah, you can like minimize this leakage a lot, but obviously the smaller this difference between these 2 energies is, the bigger an issue this is. So the issue with these superconducting circuits, this implementation that I showed you here is specifically the fact that this difference is a bit too small. But there are ways of doing these superconducting circuits which are going to give you bigger differences in these energy levels, but they're going to have their own issues kind of then.
What kind of issues?
For example, the transition frequency is going to be very, very low. And the issue is that like we can only cool it down to 15 millikelvin, and if the transition frequency is close to 15 millikelvin, you're going to get thermal populations, which you don't want to have, because thermal populations are, in this kind of language that we had in the beginning, is basically a probabilistic bit, right? Because it has a probability of being in a 1, probability of being in 0, and this is not quantum. So these are kind of mixed states then.
Thank you.
Any other question? So I have a question of my own. When you showed these Maxwell equations and how the electromagnetic radiation travels around the circuit, is it possible that when you want to control one, you also control another qubit?
Yeah, that happens basically. So here you can see that like, this color bar is really the electric field, and you can see that like this would be 0, and this is light blue, so this is not 0. So what happens is like, if you do a single qubit rotation on one qubit, you might have like a very, very small rotation on the other qubit. So maybe we didn't really talk about the parameters of this pulse that you use for single qubit rotations. But I think it's kind of obvious that like if you have a large amplitude of this pulse, what you're going to do is go from here to here. And if the amplitude is too large, you're going to already drive it back down. If the amplitude is a bit smaller, you only go from here to like halfway. You're going to be in the superposition state. But yeah, the issue is that what we're basically going to implement on the other qubit is a very, very, very small pulse. So it's going to go from here to like a little bit above, somewhere around there. And this is not optimal. But again, this is where the kind of art of circuit design comes from. There are people who do these like electromagnetic field simulations for these superconducting circuits to make sure that these effects are minimized as much as possible. But yeah, there's a lot of different things that they need to consider in these models. That's why I said that like these lumped elements are not the whole picture.
Thank you. Any other question? If not, let's thank again the speaker. So now we have a break, a coffee break again outside, and if you are coming to the dinner on Thursday and you haven't filled the form yet, please contact me and I can send you the link of the form. If not, tonight, until lunch, it's the last time to register for the dinner. Okay.
How do I turn this off, by the way?